Hi, everybody. I wanted to run through the section 7.1 in class with you. It says that the vending machine, I think that's blocked out by my face. Pause this, get my face. Okay, face gone. A vending machine automatically pours soft drinks into cups. The amount of soft drink dispensed into a cup is normally distributed with a mean of 11.5 ounces and standard deviation of 0.5 ounces. So that means it's going to follow a normal distribution. And in the middle of the normal distribution is going to be the mean 11.5 ounces. And then if I go to the right or to the left, one standard deviation, and that's where I have that inflection point or transition point, I'm going to move 0.5 higher. So that would be 12, and this would be 11. All right, so examine the figure below and answer the following question. So they've asked us, estimate the probability that the machine will overflow a 12-ounce cup. So we saw that in the middle was 11.5 ounces. So over here is 12 ounces. The probability that the machine overflows a 12-ounce cup is going to be the area that I'm about to shade in red to the right here. So that area is going to be, well, I guess I've got 50% of all the area to the right here. So the area from there to forever is 50%. And I'm lopping off this area, which I'm going to do some red cross or red slashes on. So that's 34%. So if I take 50% and subtract 34%, the probability that we overflow a 12-ounce cup will be 16%, or 0.16. Now they want to know the probability that the machine will not overflow a 12-ounce cup. Well, that's going to be the complement, so I could just do 1 minus. That's going to be the area to the left of 12 ounces that gets dispensed. That's going to be 1 minus 0.16, or 0.84. The machine has just been loaded with 1,100 cups. How many of these do you expect will overflow when served? Well, expectation is what happens when we multiply probability times the number of possible cups. So the probability of overflow we said was 0.16. I multiply that times 1,100. I get 176. So of the 1,100 cups, we expect that 16% of them, or 176, will overflow. The incubation time for Rhode Island red chicks is normally distributed with a mean of 26 days and standard deviation of approximately 3 days. Look at the figure below and answer the following questions. If 1,000 eggs are being incubated, how many chicks do we expect will hatch in the following time periods? So from 20 to 32 days. So over here, this is 26 was the mean. The standard deviation was 3. So that makes this 23, this 29. If I move 1 standard deviation left, 1 standard deviation right, and then this 32 and this 20. So I'm looking for the area between mu minus 2 sigma and mu plus 2 sigma. Via the empirical rule, that value is 95%. So we would take 0.95 and multiply it times the 1,000 eggs. So we would expect 950 of the 1,000 eggs to hatch. All right, from 23 to 26 days, I believe this was 26 at the top. Standard deviation was 3, so this is 23 and this is 29. So the probability that 1 egg hatches between 23 and 29 days would be 68%. I'm going to multiply 0.68 times the 1,000 eggs and get 680. So of the 1,000 eggs, we would expect 680 of them to hatch between 23 and 29 days. All right, 26 days or fewer Well, this is the mean, 26. Half of the area is to the left and half of the area is to the right. So we would expect that half, or 0.5, of the 1,000 eggs would hatch in 26 days or fewer. So that's going to be 500. All right, 17 to 35. So if this is 26 in the middle, I'm just going to go up 29, 32, 35. So that's here. And then I'm going to go to the left, 23, 20, 17. So we're looking for the probability that an egg hatches from 17 to 35. That's from 3 standard deviations below to 3 standard deviations above the mean. So that's going to be 99.7%, 0.997 times the 1,000 eggs. So we would expect 997 Rhode Island red chicks to hatch. That's a rough 9 in the middle. Sorry about that. All right, I'm going to pause this real quick and open up the section 7.2 one. Hold, please. Okay, so this is the section 7.2 in class. Section 7.2 we covered towards, whoa, kittens running through the room. Section 7.2 we covered during the end of class. Here they say let X equal red blood cell count in millions per cubic millimeters of whole blood. For healthy females, X has an approximately normal distribution with mean 3.3 and standard deviation sigma equals 0.3. They want us to convert the interval 4.5 is less than X to a Z interval. So all we have to do here is take 4.5. So that's my X value. And I want to convert that to a Z-score. So in order to convert something to a Z-score, I need to use the formula Z equals X minus the mean divided by sigma. So 4.5 as a Z-score will be Z equals 4.5 minus 3.3. It's supposed to be a 3. Divided by sigma is 0.3. So that will be 1.2 divided by 0.3, or 4. So the interval, all X values that are bigger than 4.5 is the same as the interval, all Z scores that are bigger than 4. All right, part B asks me to convert the X interval, X is less than 4.2 to a Z interval. So we're going to use the formula again, Z equals X minus mean divided by sigma. So this will be 4.2, as we're converting this value to a Z-score. 4.2 minus 3.3 divided by 0.3. So this is 0.9 divided by 0.3, or 3. So the X interval, X is less than 4.2 is the same as the Z interval. Z is less than 3. So we're just changing X scores to Z scores using this formula. The Z score is how many standard deviations away from the mean an X score is. All right, here we need to convert 2 different Z scores. So first, 4. If I convert 4 to a Z score, I get Z equals 4 minus 3.3 divided by 0.3. That's going to be 0.7 divided by 0.3, or 2.3333. We always round Z scores to just the 2 decimal places. So I'm going to put 2.33 over there where the 4 was. And then for 5.5, the Z score is going to be 5.5 minus 3.3 divided by 0.3, which is 2.2 divided by 0.3, which is 7.33. All right, and we're going to go to a part 2 video in a couple seconds. See you in part 2.